Lesson 5.3, forces in two dimensions. Okay, so let's say you have a box, and this box is on a surface, and you decide to pull the box with a force like this. And this, let's call this force F. And let's say that this force F makes an angle of, I don't know, 60 degrees with the horizontal, right? Or forget 60 degrees. Let's say makes an angle theta with the horizontal, right? What we could do to this, since when you look at this, you're going to say, okay, where is this force pulling? It is pulling to the right and it's pulling upwards. It's doing both at the same time, right? So what we can do is we can break this force down, any force that is at an angle, right? We can break it down to two components. What we mean by components from the word itself, component just means parts. I can break it into two parts, an x part and a y part. Okay, so let's write the x part first. So this is the x part. Let's call it fx. And I can break it into a y part, which I can call fy. Now, as you can see, this makes a right triangle. So if I wanted to find out what is fx, right? Fx here is the adjacent, right? So I can say cosine of theta is equal to fx, because fx is the adjacent. So equal to fx over the hypotenuse, which in this case is the force itself before I cut it into components. And then I multiply by f on both sides. I get that f of x, and this is important, f of x is equivalent to f, which is the original force, multiplied by cosine of theta. Similarly, if you go through the same process for y, except instead of cosine of theta, you use sine of theta, you will get that f of y is equal to f sine theta. And as you can see, since this is a right triangle, if I had fx and fy and I wanted to get the resultant, right? The resultant is just the big force that I split into fy and fx. So if I wanted to get f, then I'd say that f squared, Pythagorean theorem, right? F squared is equal to fx squared, x squared plus fy squared. Put a radical on both sides, you'll get that f is equivalent to radical fx squared plus fy squared. The next thing you're going to want to learn how to do is adding two vectors, right, or two different forces. So say I have, this is F1, right, and then I have another force, let's make it a different color, let's say this is F2, right, or, let's make it a bit more interesting, let's say this is F2. And I want to add these two together. Now, all you have to do in this case is just take these two vectors and place them head to tail, right? So this is F1, all right? And then take the head of F2 and put it at the tail of F1, or the opposite. So let's take, I'll do the opposite. I'll take the tail of F2, I'll put it like that. And then the resultant, right, the force, if I wanted to add them, right, the net force, this is F2, The net force would be from the tail of this one to the head of that one again. This is the net force in orange. This is F net. That's how you add them. And if you're wondering how can I get the value of F net, or what's the magnitude of F net, right? All you'd have to do is say F net x. You have to calculate F net x, which would be F1 x. So this would be it would be F1x plus F2x. Alright, that's F net x. And then you'll find F net y. So you're going to say F net y. And similarly, that will just equal F1y plus F2y. And then, as you saw in the previous slide, or a few minutes ago, F net will be equal to radical F net x squared, so its x component squared, plus its y component squared, so F net y squared. That's it. That's how you find the magnitude of F net. Okay, so let's take an example about vectors, right? So let's say you have a box, and this box is on a frictionless surface, right? And this box has a mass. This box has a mass equal 40 kilograms, right? And you decide to pull on this box with this force right here of 200 newtons, which makes a 30-degree angle with the horizontal. And then I tell you that this box is not moving on the y-axis, and I want you to calculate its movement on this surface. So I want you to find this box's acceleration, right? So now all you have to do is you're gonna say F net equals ma, and then you'll substitute m, it'll just become 40. So this is just 40. This is 40. And then F net will be your force on the x-axis. So it'll be this thing right here, the x component, right? And as we know, this component right here is just going to be 200 cosine 30. So we're just going to say 200 cosine 30 degrees is equivalent to 40a, and then you just divide by 40 on both sides. You'll get that a is equal to it's about equal to 4.33 meter per second squared. Okay, so next thing we're going to discuss the concept of an equilibriant. Now, an equilibriant is just a force that balances all the forces acting on an object. So say this is your block, and you're pulling on this block like this with the force of, say, 200 newtons, and this is like 30 degrees. And you're also pulling with, say, another force. You're pulling with this force right here. And this force is like 50 newtons. and we can add the third force, but it's going to be the same thing. So what how can I balance all these forces with one force? Because an equilibriant is a force, it's one force that balances all the unbalanced forces in your free body diagram or in your scenario, right? So for me to do this, all I have to do is I have to find f net, right? I need to add these two vectors to find out how much do I need to balance. So again, if we take these two vectors and we put them head to tail, so this is the first one, this is 200, right? And then the second one would be like this, so like 50 newtons. Then F net would be this force right here. Okay, this is F net. So the way we do this is we calculate F net x and F net y, right? So to calculate F net x, we're just going to say F net x is equal to the x components of both of them. So the x component of 200 of the first one is just 200 cosine 30. So it's 200 cosine 30. And for the other one, you could just consider the angle to be 0. So you can say this is plus 50 cosine 0. And this would give you f net x is equal to 200. This would give you 223. So f net x would be equal to 223 point, or you know what, let's just keep it 223. And similarly, you do the same process for f net y. So f net y is equal to 200 sine 30. So 200 sine 30 plus 50 sine 0. And by the way, you can notice here that since it's sine 0, this is clearly only on the x-axis, and you don't need to write plus cosine 0 and plus sine 0, but using it as angle of 0 works because sine of 0 just equates to 0, so this wouldn't really exist. But do whatever way makes you comfortable, right? So you get that f net y is equal to 100. F net y is equivalent to 100, and so you get that f net now is equal to radical 100 squared plus 223 squared. And this gives you about 244. So that's the magnitude of f net, right? So the equilibriant would have the same magnitude as f net, right? If I want to balance f net out, I just take the same magnitude of f net but flip its direction. So the equilibriant would just look like this. This would be the equilibriant. That's the equilibriant. And the equilibriant has force equal to 244 newtons. Okay, now let's talk about inclined planes. Right, so this is an inclined plane, and you have an angle of theta here, and then you have a box that is okay, and then you have a box that is on top of this incline, either going up or going down. In our exercise, we're going to consider that you just put it on the incline and now it's sliding, right? So what are the forces on this incline if we say it's a rough incline, right? The forces, if we draw the free body diagram, are you're going to have friction, you're going to have friction this way, so this would be FRK, kinetic friction specifically because it's moving, and you're going to have the normal force this way, this is the normal force, and then you might say, well, what pulls it down? Okay, so if you look at this diagram, you also have the weight of the object, right? You have Fg, but Fg is not pointed perpendicular like the normal forces. Fg is just going to be pointing straight down, right? So what we do usually is we take the coordinate plane to be where the normal and FRK are. So we take this to be our y-axis, so this is the y-axis, and this is the x-axis, right? So right now, what looks like it's tilted, because we tilted our entire viewpoint, right? It looks like FG is tilted. So it looks like FG is making an angle, right? And so when a force makes an angle, we can break that force into components. And that's what we do here. We break FG into two components, and we say that FG has a component right here that goes this way, and this is FG sine theta. If you're wondering why it's sine, you just play a bit with the triangles. It's some geometry, and you'll find out that the angle theta would be over here, or if you want to use this exact angle, it would be over here. So then sine would be this, what's pulling it downwards, right? And the component of Fg that's directly opposite the normal force would be the cosine. So this right here would be Fg cosine theta, where theta is just that same angle of the incline. Okay, so let's solve this following scenario. It wants T2 and T1, and you have that the mass is equal to 2 kilograms. So the mass is equal to 2 kilograms, and this object is not moving, it's held at rest. So what that means is, let's draw the forces, or the components of the forces of T2, right? Because T2 has an angle, so it has components. So the first component we can draw is we can draw the y component. So this thing right here will just be T2y. And we know that T2y is going to be what? T2 sine theta. And T2 also pulls to the right. This component right here can be referred to as T2x, which is T2 cosine theta. Right? Since this is at equilibrium, we can say whatever is up is equal to whatever is down, the forces, and whatever is to the right is equal to whatever is to the left. So T1 in its entirety, right, is equal, T1 is equal to T2. Let's change the color for T1. Let's say T1 is equal to T2x. It's equivalent to the x component. And we know that the y component of T1, T1y, is equal to Fg. It's equal to the weight of this ball, right? Equal to Fg. So now we can solve for T1y. So T1y, which we know is just T1 sine 50, is equal to the mass, which is 2, multiplied by gravity, which for the sake of ease of calculations, we're just going to consider gravity to be 10. Now you can divide by sine 50 on both sides, and you'll get the T1 is equal to 26 newtons. Now, using the fact that T1 is 26 newtons, I can calculate using the fact that T2, this is all T2y, T2 sine 50, T2 equal to 26 newtons. Using the fact that T2 is equal to 26 newtons, I can now solve for T1, right? So that means that T2x, right? T2x is equal, this entire thing, T2x is equal to 26, which is T2, multiplied by cosine of 50, and that entire thing is equal to T1, which means T1 is equal 26 cosine 50, which is 16.7 newtons.
That'll be it for lesson 5.3, forces in 2 dimensions. If you have any questions or want to ask anything at all, you can ask it down below in the comment section or in the server. And yeah, good luck.